Okay, logarithmic functions. Logarithmic functions are actually just the inverse of exponentials. So if you have a log of base b to the x is equal to y, is if and only if b to the y is equal to the x. So you can see this is where the inverse aspect of an exponential comes into play. So we'll kind of use these interchangeably to look at our first portion, which in the instructions it says to write each one of these in opposite fashion, meaning we're going to write this one as a logarithm, and then a problem like these we're going to write as with exponentials. All right, so 1.2 cubed equals m. So just looking at this, you can see that base b, and here's b right here on the if and only if of b to the y, and that would be our base b, which is 1.2. So we know it's going to be log of 1.2. The 3 would be the y in our equation up there. And then our m, well, our m is like our x. So it's log base 1.2 of m is equal to y. All right, let's look at the next one. E to the x is equal to 9. So on e, first of all, e is our base again, it's just like the b's. So we would say log, but there's a special one for e. Since it's e, we actually call it the natural log, and it's understood to be there. I'm going to write it here this first time, but actually anytime you write ln, it's just understood to be base e. Right? The x that we're raising the e to is the y spot up here, so it's going to be equal to x. And then our 9 is the leftover portion. So ln of 9 is equal to x. And just to make sure you guys understand it, I could rewrite that as just ln of 9 is equal to x, because like I said before, e is understood to be the base on natural logarithm. All right, now we have log base b of 4 is equal to 5. So we can write that as an exponent. We'll take our b, raise it to the 5th power, and it's going to be equal to 4. So now we've written it as an exponent. And then our next one, remember this is understood to be base e for ln, so that would be e to the negative 3 is equal to a. And if you wanted to, we could rewrite that as 1 over e to the 3rd is equal to a in order to get rid of the negative exponent. So now we're going to look at these and try to solve them, actually solve the equations instead of just rewriting. So using our logarithm property we did before, definition of logarithms, you could say, I guess, is just, remember it's 5, our base to the 2nd power. So 5 squared is equal to x squared plus x plus 4. And now we can just solve this algebraic equation like normal. 5 squared is 25. We'll isolate, or we'll set it equal to 0 rather. It's an equation we try to solve by factoring. We're not able to, so we're going to go to the quadratic formula. So we know that x would be negative b, so negative 1 plus or minus the square root of b squared, so 1 squared minus 4 times 1 times negative 21, or c, all over 2 times our leading coefficient of 1. All right, so what we have here, we have negative 1 plus or minus this 21, this 4, so make an 84, right? So we have 1 and then 2 negative make a positive. All over 2, so it looks like our answer is going to be negative 1 plus or minus the square root of 85 all over 2, which is, if you could write that as a decimal if you wanted to using a calculator, but for right now, this would be good for us. These 2 particular values. All right, let's look at the next one. Part F is log of base x of 64 is equal to 2. All right. So we know that x squared is equal to 64. So just using algebra, we could say, well, x therefore has to be plus or minus 8. So let me go ahead and just write it like this, 8 or negative 8. We have to be careful with this one. And really, this other one we could have checked as well, but this one we're looking at it, if you go back and you plug these in, well, if you plug positive 8, that'd be base 8, which is fine. If you plugged in negative 8, you'd have logarithm of negative 8. And we can't have a negative with logarithms. They're actually not even functions. It goes in the same thing with exponentials. You can't have like a negative number with exponentials. So the only x value that works here is 8. All right, so our next one, e to 2x equals 5. And remember that we have, our log base b of x is equal to y, and that b to the y is equal to x. So for this particular problem, we'll solve these a little bit different later on, but this is all we had to, for our extent of our knowledge is this piece right here for logarithms. So we can make this piece, which right now is this form, b to the y equals x, look like a logarithm. So our log, it's base e right now. So just going back to what we did earlier, 5 is equal to 2x, right? So that would become e to 2x equals 5. Well, log base e is the same thing as natural log, right? So it's just natural log of 5. It's equal to 2x. Remember, it's just natural log is the same thing as log, except it's understood base e. And so to solve for x, we just have to simply divide by 2. So we know that the ln of 5 over 2 is equal to x. All right, next one, h. We would take 3, raise it to the power of 2x plus 1. And that's equal to 243. Well, remember from exponents last time, when we have these, we can solve them if we would try to get a common base. So we know that 3 to the, 3 squared is 9, 3 thirds 27, then it's 81, so it looks like it's going to be 3 to the 5th. Would be 243. So now we have the same base. We just need the exponents to be equal. So we're trying to figure out what value of x would make this entire exponent right here equal to 5. And it looks like it's going to be x equals 2. Would work for that particular problem. Let's look at a graph now. I'm going to take, first of all, this f of x equals log base 2 of x. It's going to be our parent function for these next two problems. Let's rewrite it as, so I'm just come over here. Let's rewrite it as log base 2 of x is equal to y, which we know that means 2 to the y is equal to x. So if you're thinking about it in these terms, you're thinking what kind of values for x would be nice if we take 2 and raise it to some power. And it's going to help us kind of develop our table a little bit. So you might think about, well, is there a way for us to get an x value of 0? Well, no, there's not. You can't raise 2 to any power and get 0. But another one you might think of, is there a way to raise 2 to some power and get 1? Well, yeah, that'd be if y was 0, right? Because it'd be 2 to the 0 is equal to 1. So letting x be a 1 is good. And we just said that if you went 2 to the 0 power, that would give us 1. So that means that 1 comma 0 is a point. Well, is there a way to raise 2 to the power and get 2? Well, yes. If we had x is 2, we had to raise 2 to the first power, would give us 2. So we know that log base 2 of 2, right, is equal to 1. So that's that point. Is there a way to raise 2 to some power and get 3? No. About 4? Well, yes. We know that 2 squared would be 4. And then the next one would be 8. So log base 2 of 8 is equal to 3. And I think it'll help us if we kind of go back one as well. I think there's a nice one right here, is there a way to get 1/2 for x? Well, yeah, that'd be if we put in 2 to the negative 1, we know is 1/2. So there's a few points for us to kind of plot now. So 1/2, negative 1, 1, 0, 2, 1, 4, 2, and 8, 3. Wasn't sure if I had that one plotted. I did. There you go, and 8, 3. And then if you continue to pick, like if you said 1/4, for instance, for x, that would be 2 to the negative 2. So you know that way over here, you know, is the 1/4. And in fact, it's just going to continue to get closer and closer and closer. But remember we said earlier, there's no way to raise 2 to some power and get 0. So that's where that vertical asymptote comes into play. And so here's our graph right here. All right, and since we talked about vertical asymptote, we'll go ahead and just put it in red. It's our y-axis. So kind of like with exponentials, it's probably a good idea to graph that vertical asymptote first. But for our first problem, I just want to kind of do it this way. But having that vertical asymptote plotted helps us out a lot with it, especially when we start doing transformations. All right, so looking at domain, it goes to the left. It gets really close to 0, but doesn't touch it. And then it goes to the right forever. The range, it goes down forever. And it goes up forever. So negative infinity to infinity. And then our domain 0 to infinity. Vertical asymptotes, that means it has to be x equals. Is x equals 0 for this problem. The limit as x approaches 0 from the right. We don't really care from the left because obviously we have no graph to the left. There's no way for us to get over here and have negative numbers. All right, it's like you can't raise 2 to some power and get a negative number. So as we approach 0 from the right, it looks like we're getting really close to negative infinity. And then as x goes to infinity, f of x approaches infinity for our final limit. For our second problem, I went ahead and wrote the table from our parent function log base 2 of x, because this is the exact same log with the same base 2. All we're doing is we're shifting it with this x minus 2 and then shifting it again with this plus 1. So the minus 2 is going to take our graph and shift it to the right 2, and this plus 1 is going to shift our graph up 1 unit. So using our transformation table, we just add 2 to the x's and add 1 to the y's. So we have 2.5, 3, 4, 6, and 10. And then we're going to add 1 to all of the y's. So negative 1 plus 1 is 0. And then we have 1, 2, 3, and 4. Plot our points. So 2.5, 0. There's our x-intercept. 3, 1. 4, 2. 6, 3. Now we're able to fit in the 10 this particular time. And then our graph has those points. And like I said before, I didn't do it this time, probably should have. Finding that vertical asymptote is probably a really important step. So remember our vertical asymptote in our previous problem, we'll go up here real quick, is x equals 0. So that vertical asymptote is going to shift to the right 2 and up 1. Well, up 1 doesn't really do much to a vertical asymptote, but the right 2 certainly does. So typically it's right here at x equals 0, like we said before. It's going to shift it 2 units to the right. So you know our vertical asymptote is that line right there, that vertical line at x equals 2. And that's what our graph's going to get really close to without touching. And obviously it's going to connect with those other points and continue to increase and go to the right. So filling in our information, our domain, well, it's a little bit restricted. It's going to be 2, non-inclusive, to infinity. Our range is negative infinity to infinity. Vertical asymptote, we know is x equals 2 because we shifted the graph to the right 2. I'm going to skip this one and come to this very last limit. First of all, limit as x approaches infinity. It's going to be infinity. And this time it's blank because I want to see if you can figure out that missing piece. Well, if we shifted it to the right 2, obviously 2 is the number that we're going to be looking at, that around that vertical asymptote, what's occurring. And it's only coming from the right that we're going to be looking because there's nothing on the left side of 2. So as x approaches 2 from the right, it's getting closer and closer to negative infinity. That's the y value we're approaching. All right, letter C is a natural log graph. I don't want to overthink this one. I'll do a little bit like we did earlier. Remember, that's the same thing as saying ln of x is equal to y. So e to the y is equal to x, because remember, it's a natural log, has a base e. Now we can go ahead and do all those values we did earlier. I just think that's kind of a make it a little more difficult than it needs to be. Let's just go the values that would be nice, like, for instance, x. Is there a way to get 0 for x? Well, just like earlier, no, you can't raise e to some power and get x, or get 0. Is there a way to get 1? Well, yeah, we can get 1 if we rose e to the 0 power, so e to the 0. So 1 comma 0 is a point. And then let's just do one more. Let's say, is there a way that we could get, e for the x, for instance? Well, e to the first power would be e. And remember, e is approximately 2.718. And then now we're looking at, is there a way for us to go, the other direction? I'll write this 2.71 out here. So remember, that's approximately 2.718. Well, if we want to go this other direction, maybe you want to think, well, I'll write this one so you can see a little bit better. E to what power is equal to e to the, -1, for instance? Well, that would be if this spot was also -1. So we know that e to the -1, or 1 over e, is when y is -1. And really, that's just me kind of showing you how you can get a fraction over here. So 1 over approximately 2.718, which is, between 1/2 and 1/3. And, getting other points really just kind of making it difficult. So just plotting our points here, we know that we had the point 1, 0 is a point, and then E1, so 2.718 to the right, up 1 unit, and then 1 over E, which remember is between 1/3 and 1/2. So for this particular one, we're going to go down to -1. Roughly about there is good enough. And then our vertical asymptote, like we said earlier, we can't get 0. And then we know that it's going to apply. So it's just like the logarithm one we did earlier, except we have a base e instead. So our domain is everything from 0 to infinity. Our range is all real numbers. Vertical asymptotes, x equals 0. The limit as x approaches infinity of f of x is infinity. And then the x value we're looking at here for the other spot around our vertical asymptote is 0. We're going to look at it only approaching from the right. And it looks like it's going all the way down to negative infinity. Final graphing problem. Have a transformation. So we have our natural log of x table written. Now we're going to have our transformation. So the negative on this x is going to change our x's by multiplying them by -1. And the negative on the outside is going to do the same thing to the y values. So basically, we're just changing all of the signs we have on our problem here. And now we're going to make our plot, which, let me, just to keep this a little cleaner, apologize, guys. Let me take that out real quick. All right, just try to save some time right here. This graph's going to be a little bit different. So I'm going to put our vertical axis over here. I apologize. So there we go. This is our new y-axis. Disregard this little scribble mess I got here. And then, of course, our x-axis is right here, because you can probably see what's going to happen already. So we're going to be heading in the negative direction this time. So we don't necessarily need the right side of our graph per se. So -1 over E1. So just like we did earlier, it'll be about right here. -1, 0. Plot that point. Negative E, remember, which is approximately -2.718. So -2.718, -1. And then there's our graph. Once again, vertical asymptote. We're not doing any type of shifting left or right. All these reflections are not going to change anything as far as our vertical asymptote is concerned. So our vertical asymptote is still all of those pieces, or still the y-axis. So now we can make our graph. And there we go. All right, so our domain, negative infinity to 0, not including 0. Our range is negative infinity to infinity. Vertical asymptote at x equals 0. The limit as x approaches infinity for f of x, which is what I believe is on your paper. Well, here's an issue with this one. We can't have x approaching infinity because it doesn't even go past 0. So really, let's go down here on your papers. Make sure you do it on your notes as well. Let's change that to negative infinity. So as x approaches negative infinity to the left forever, it's going to continue to go down. So that's negative infinity. And then our vertical asymptote is 0. So that's the number we're concerned with. And it's the first time, every time we've done these, it's been as we approach 0 from the right. As you can see, there's nothing on the right side of our graph. So it's going to be everything as x approaches 0 from the left. So as we approach 0 from the left, looks like our graph is going to continue to go up, right? So that means that our limit as x approaches 0 from the left is of f of x is infinity. All right, let's finish up with some mixed practice. So here's our given function, g of x. First part is what's g of 40? So g of 40 would be log base 3 of 2 times 40 plus 1 minus 2. So we're looking at log base 3 of, well, 2 times 40 is 80, plus 1 is 81, minus 2. So remember, this portion right here, this log base 3 of 81, right, let me go here to the side, we're saying that 3 to some power, we'll just call it x for right now, 3 to some power of x is equal to 81. Well, 3 squared is 9, 3 to the third is 27, 3 to the fourth is 81. So we know that log base 3 of 81 is 4, because 3 to the fourth would be 81. And then have minus 2, of course. So g of 40 is equal to 2. All right, part B is asking for what point. So for g of 40 is equal to 2, then that'd obviously be 40, comma 2. All right, part C, if g of x is equal to 3, what is x? So we know our function, so 3 is equal to log base 3 of 2x plus 1 minus 2. So now we're going to solve this equation. Well, we can add the 2 over. So log base 3 of 2x plus 1. We know that 3 raised to the 5th power would be equal to 2x plus 1. So 3 to the 5th power, we did 3 to the 4th earlier, was 81. So 81 times 3 is 243. It's equal to 2x plus 1. So subtract our 1 over. That's 242. So it looks like x is going to be 121. I believe part D is asking for the point again. I'll double check it momentarily, but I'm pretty sure of that. So if x is 121, that occurs when g of x is 3. So that's our point, 121 comma 3. Our last things are on this number 1 mixed practice is the limits, which you can probably get the answers pretty quickly. But I do want to take this. I just rewrote g of x over here to the left. We could rewrite this. Obviously, still log base 3. And I'll put brackets because I think it'll make it easier to see. Hope I can squeeze it all in here. And we're going to take that 2 and factor out our 2 like we have on all other function types this year. So that'll leave us with an x plus 1/2 now. All of that is inside of our logarithm, and then we have our minus 2 at the end. So if we were doing a transformation table, remember we'd always do the opposite with these x's. This would be multiplying by 1/2. This would be shifting it to the left 1/2, down 2 for the y's, all that kind of stuff. With log base 3 obviously is our parent function. But this 1/2 is the important part right here. So we know that plus 1/2, remember, it shifts it to the left 1/2, which means our vertical asymptote, which is typically x equals 0, our vertical line, is also going to be shifted to the left 1/2. So our vertical asymptote for this problem is x equals negative 1/2. That's going to help us solve these problems. So obviously we don't have any reflections. This is just shifting it left and right, some multiplying with the x's. But other than that, it's not doing any type of flipping like we did in our last problem on the graphing. So as we get bigger and bigger and bigger with our x's, and we can see it from the points we found in the prior pieces of this mixed practice, it's just going to continue to get bigger y values. So as limit as x approaches infinity of g of x is still infinity. This is the interesting one. So remember, we left this x approaches blank. It's what's going on around the vertical asymptote, which this time our vertical asymptote is negative 1/2. So I'm going to fill that negative 1/2 in. And then our graph's going to continue to go down forever. Remember, there's no reflections or anything like that. So that's where our negative infinity comes into play. But find that negative 1/2 was kind of the tricky part for that limit. All right, final problem is just a piecewise function. I'm going to graph this right portion first. If ln of x, if x is greater than 0, and just, I know I've talked about this before in class, but just when we're dealing with logs, remember ln is just a specific type of log, special log. It's 1, 0, right? Because it's log. So for ln of x, we know it's going through 1, 0. And we know that's going to have this vertical asymptote that gets really close to, and then it starts to flatten out. We've done enough of these problems now where I think we know that's pretty much what it looks like. And then the ln of negative x is the exact same thing, except it's reflected across the y-axis. So it's going to go through negative 1, 0. And then hopefully I can draw this somewhat close. It's just going to the left. Both, of course, having that vertical asymptote once again at x equals 0 that it can't touch. So now we're just going to answer the questions that I've had you do for the domain. It's negative infinity all the way to 0, non-inclusive, and then 0 to infinity. A range, it's going down forever and up forever, so it's all real numbers. So I'll just write an interval notation, negative infinity to infinity. Vertical asymptote is x equals 0. That little red line I've drawn in there. The limit as x approaches infinity of f of x. It's going to continue to go forever to the right and up. So it's infinity. And the limit as x approaches negative infinity of f of x. It's going to continue to go to the left, right here, and up. It's coming from that direction. So it's negative infinity. And that completes our logarithmic function notes. Next time we'll get into logs a little more deep. You guys have a good one.